All right, everyone. So continuing with uh, investigation of the Faraday's law, here we're going to talk about how if we take a conducting loop and we place it in a uniform magnetic field, as long as the field is not changing, there's nothing will happen to the conducting loop. But let's say the magnetic field that is into the page starts changing. Remember, if the magnetic field starts changing, then the magnetic flux through the center of the loop will start changing. And then we know, right, that there will be induced EMF, which will equal to negative N. And this is just one loop. We can just say that N equals 1 here. So, but changing magnetic flux as a function of time. And there will be induced EMF and induced current. Okay. So, one of the things we have here is in terms of then when there's induced EMF, induced current, remember, we talk about that current is flow of charges. But remember, what does um, act like a driving force for the charges to flow in the same direction? Well, remember, electric field, right? That means whenever we say, and we can see from here, right? So think like this. If the magnetic field is into the page, so this is B in, right? And then we have dB dt, which is greater than 0. That means magnetic field into the page starts increasing, which means that the loop is going to try to oppose that increase in magnetic field into the page by constructing its own magnetic field that will be out, which is in the opposite direction. Because remember, the goal of the induced magnetic field, so input like here is B induced, is going to be out of the page because into the page magnetic field is increasing. So it's going to oppose by supplying more magnetic field or pumping more magnetic field out of the page, try to oppose the increasing magnetic field into the page. And that can happen if the current here is induced current, right, is counterclockwise, as you can see, right? Because what we do, remember, we have our thumb is in the direction of out of the page. Remember, using the right hand rule, we can determine the direction of the current because we want magnetic field out of the page. That's kind of, given to us because into the page magnetic field is increasing. Then to have the thumb out of the page, then we have to have our fingers, right, kind of curling in the direction of the, sort of like, let's say, magnetic field. Sorry, fingers curl in the direction of the current, which will be clockwise. So this is my way of like writing the curling of your fingers where the thumb is pointing out of the page. All right, so that means the current counterclockwise, but again, the current is due to some kind of electric field. Remember, every time you have a current is because charges are being pushed. Who pushes those charges? Electric field. That means we can say that there is also an electric field generated in that loop. An electric field, you can think of like, let's say there's a field line that's going to be like this. Let me do a different color. So there is a field line that will be like that. And electric field, remember, is always tangent to those fields, right? That means we have like, let's say 1, 2, 3, 4 different positions where I can find electric field, which is always going to be tangent to the loop. Okay, that means there's electric field generated due to the change in magnetic field. Now, if we then talk about in terms of the work done by this electric field on the loop in moving a test charge once around a loop, remember the work done is equals to Q times E, right? So charge times, well, where the Q is the test charge, you can write Q naught if you want. E is the potential, right? Or the potential difference of the EMF. So that's the work done. W is equal to Q times EMF. Now, the work done on a charge by the electric field is then Q times E times 2 pi R. Okay. That means the test charge magnitude, electric field, and then this is the circumference of the loop. Okay. Remember, we can look at it in terms of this, right? So this is equals to force times displacement. delta S. Remember, that's kind of like, let's say, the equation for the work done, force times delta S. What is that force? What is the electric force doing work? It's Q times E. What is the displacement? It's 2 pi r if it's one cycle. Okay. Then we can say that, well, the work done for those both equations are, basically equal to one another. So we can say then QE, Q times EMF, not E, Q times EMF from the first version of the equation equals QE 2 pi r from the second version of the equation. Here you can see, right, Q cancels out, and then we rearrange and we get E equals electric field, E equals EMF divided by the circumference, EMF divided by 2 pi r, which is, I never remember we talked about this type of equations. E equals delta V over D. It was, in this format, right? Electric field is potential difference divided by the distance. It's just now potential difference given in terms of induced EMF, and distance is the circumference, so we'll write it as 2 pi r. So this is not a new equation. We have looked at this equation for other type of different configuration, but this is specifically for the um, induced current, induced EMF due to the change in magnetic field through that, through the loop. All right. So if we then take this equation and apply when we say that, okay, so then induced electric field is, so remember, so we're saying electric field is equals to EMF over 2 pi r, but remember EMF, this is the induced EMF equals negative change in magnetic flux over time. Then I can replace this EMF with that and basically have this equation where I'm just basically replacing EMF with, change in magnetic flux over time, a negative of change in magnetic flux over time. Okay. So from here, I can see that magnetic flux, remember, magnetic flux as the equation was B times A times cosine of theta, assuming right now cosine of theta is just 1, so it's B times A. Well, if the magnetic flux is changing, it should be due to either the area changing or the magnetic field changing. Well, in this case, due to the magnetic field changing, so then I can write it in terms of this is equals to d b dt, where the area is just pi r square. And that's what we have, right? So this is just magnetic flux, changing magnetic flux. The B is the magnetic field, pi r square is the area, and d dt is just changing that. Okay. Since we can assume that radius is the same, so this will cancel with that. We can then get rid of the pi and then have this equation where electric field equals negative r over 2 dB dt. Okay. That means this is the induced electric field. All right. Now, what we have here is then this equation of the Faraday's law, this version of the equation can be modified into more general form where the EMF, induced EMF, can be replaced with this equation, closed integral of E dot ds. This is the equation that we have seen before as well, where the potential difference is equal to the integral of E dot ds. So then we can replace this equation, where the EMF is replaced with this integral. So it says the induced electric field is a non-conservative field that is generated by changing magnetic field. Okay. Now, in terms of then what we have here is the magnetic flux is changing. That means the right side of the equation is not zero. If you were wondering then why, let's say, we specifically indicate that this is a non-conservative field, well, because remember, due to this equation, the right side of the equation is changing, negative change in flux. And we know, right, the change in flux is non-zero. The left side of the equation is closed integral of E dot ds. Now, one thing we have here is we know that if this is, remember, this is equal to the work, the change in potential energy, then we can think of, like, let's say this is basically the work done by this electric field, right? We can kind of like multiply that by Q and get the work done. Well, one thing we have is that if you come back over here, well, there is a non-zero work done. Okay, then that means work done is, if you go around the loop, is not zero. where we talked about that for the conservative forces, if you go and complete a loop, your work done is zero. Because if you go from A to B, then come back from B to A, which is completing a loop, work done by conservative force always equals to zero. But here, work done by the electric field, right, is not zero, which means it's not a conservative field. So that means that's why we specifically say it's a non-conservative field, and also it's a different type of electric field. So it's very different from electrostatic field. When we have some kind of source charge and there's electric field generated by that, this is not that. This is completely different type of electric field. It has a lot of similarities, but also some differences in terms of the source that gives us this electric field, because this electric field is not due to some kind of charged particle. This is not because there is some kind of source, electric source that generates this electric field. No, this electric field is generated by the changing magnetic field, which is a new type of electric field. All right. One of the things we're going to see later on in I think chapter I think 32 or 33. So, for example, what happens if you changing, right now we have this, right? If there is a loop and you're changing the magnetic field into the page, so then there's electric field. So in that loop, in that conducting loop, there's electric field, which then drives the charges. What if I remove this loop, conducting loop from this region, but continue change the magnetic field? What happens? Well, if I have a device that will allow me to measure, for example, electric field, what I would see in this region is this electric field that I have right now for the conducting loop will still be there. That means what happens here is every time you change the magnetic field, in the same region, there is an electric field generated. Now, it just happened to be that I have a loop over there, and this conducting loop, due to this electric field, have the current. That means the current in the loop is only because there was already an electric field over there. And that electric field just affects this conducting loop by pushing the charges and inducing current. That means here's a little more fundamental than just basically you have a conducting loop and an induced current. The idea is that even if you don't have the conducting loop over there, the electric field is present because there's a changing magnetic field. Because changing magnetic field acting like a source of electric fields, this new type of electric field. So if you happen then to put a conducting loop over there, well, if there's electric field, it's going to be affected by that. The charge is going to be pushed because of that conducting, because of the electric field, and then you're going to have a current. That means current is there because of changing magnetic field generates this new type of electric field. All right, so interesting, very interesting fact. All right, so next we're going to talk about generators and electric generators and electric motors. So a lot of times you probably already have played with some electric generators in your house. If you have a, let's say, emergency flashlight or radio, remember some of those flashlights where there's like a turning crank, so you basically turn it a little bit, and then you can just operate your flashlight. Just basically when you turn like 5, 10, 15 times, then the flashlight basically can operate for maybe like, let's say, 5, 10 seconds, but then becomes too dimmed and you have to crank it again a little bit. Well, that's a pretty much electric generator. So what the generator does is converts the mechanical energy from a turning crank into electric potential energy. That means the generator requires some kind of mechanical work to be done on the system, and that system, that mechanical energy, then can be converted into an electric energy. Okay, so this is sort of like, let's say, the schematics of this type of um, generator. Okay, so now inside this generator, right, you can see that what we have here is there are two magnets facing, where you have a north and a south facing each other, which means there is a magnetic field that's going to be from north to south, let's say in this region. So there is a magnetic field like this in this region. Now, what you have here, you can see, right, there's a loop of wire. that will be um, sort of like a rotating, so that loop of wire by some kind of external means. So like let's say you're turning the crank and then you're rotating that. So as this loop of wire is rotated, then the flux, you can see, right? You can sort of like, let's say if this is your loop of wire, and let's say this is the magnetic field, as you're turning this, so let's say as you're turning it like this, right, for example, clockwise, the magnetic flux through the region, through that area, right, of the loop also changes. So that change of the magnetic flux then induces EMF. And then there's a current in the loop according to Faraday's law. Because, think like this. So if this is that, let's say, if this is that loop of wire, imagine then magnetic field is, you can see, right? So like, let's say going like this, which is sort of like, if I look at from the front, from the south magnetic, let's say from the south of the magnet point of view, then magnetic field sort of like a coming out of the page. And magnetic field is not changing, but we are rotating basically this loop. As we're rotating, right, turning the crank, it rotates, then area changes. That means you can have from something like this to maybe a little bit later, it's like that, right? So pointing like that, it's kind of like hard to do, thing like this. So let's say here's your area, then maybe here's your area, then maybe here's your area, right? So that means you're changing as a function of time. And every time you are changing the area of the loop, magnetic flux changes. As the magnetic flux changes as a function of time, then there is a EMF, induced EMF. And this induced EMF basically gives you induced current, and then there's going to be a current. So for example, in this case, if the rotation is counterclockwise, you can see, right, then for example, this loop will start rotating like that, and I'm going to get increasing flux until it's pretty much parallel, right, to this, sort of like, let's say until it's parallel like that to the magnet. That means flux is increasing. So then the loop going to try to oppose that by generating its own magnetic field, which is going to be, let's say, in the opposite direction. And, that's going to give us basically a current. Okay. So that the current basically will be, uh, in this particular case, clockwise, because to generate magnetic field, be induced, right? Be induced if it's into the page to compensate for that. When the flux is increasing, is going to be in opposite direction. But when, let's say, the loop starts decreasing the flux, then what you will have here is the magnetic field, induced magnetic field direction will change, and then the current will reverse. Okay. That means what we have here is there's an induced current, basically thing like this, right? There's an induced current because of this loop pretty much rotating. Now, what we have a commutators that are devices that are connected and allows the loop to rotate freely, and a connection from commutators. Um, you basically have some, two brush on each side that then used to connect some kind of, a flashlight or a light bulb, or, something like a radio or something like that. Okay, so those are basically give you a mean of connecting to the, let's say something that requires then this electric energy that has been converted. Okay, that means what you do here is you do some kind of mechanical work, and then that mechanical work allows the induced current to, basically that, or the turning loop, induced current, induced EMF, basically converting that mechanical work into electrical and, energy, and, operate your flashlight, for example. All right, so now one of the things we have here is that you can have two types of generators. You can have a DC generator, and then you can have also an AC generator. So then AC generator basically is specifically designed so that you're constantly rotating. constantly rotating, because one of the things we have to do here is, remember, you have to rotate that loop in order to get induced current, because as you stop, right, remember, so if you crank it, and if you stop it, your light bulb will basically dim, within like few seconds. That because all that mechanical energy was converted to electrical energy, and if you don't continue doing it, then there's no more energy, and your light bulb goes dim. Okay, so for alternating currents, then we have it consists of a loop of wire, right, rotated by some, again, external means in a magnetic field, ends of loop connected to now two, slip rings that rotate with loop, and these connections from the slip rings, which act as a terminal of a generator, to external circuit. Again, same idea, right? External circuit by those metallic brushes. That means they basically act like a terminal of the of this battery. Okay. Now that means one of the things you need to have is some kind of mechanical means of doing work. So you have, for example, hydroelectric plant, right? So you have a falling water directed against the blade of the turbine, produces rotary motion, or you can have you can write a steam, the energy released by burning natural gas used to convert water to steam, then steam directed against the turbine blades, or you can have a wind, right, turning the blades and things like that. But the idea here is what we're doing here is we are converting the mechanical energy into electric energy. Okay, so and we are kind of like, in order to continuously have energy, there has to be continuous rotation. Okay, so one of the things we have here is that if you're dealing with an alternating current, which is given as AC, so DC is the direct current, and AC is an alternating current. Okay. Now, for alternating current, then you can see that if you considering this as a loop, and then we can put more several loops together. What we have here is magnetic flux is equals to BA cosine theta. Okay. Now, when it's rotating, then we can assume that as it's rotating, so let's say this is being normal. Technically, that's where area A is, right? And this is being the theta. As the flux changes, so d dt, so this is basically d dt of this whole thing. So in a way, what changes here is the angle theta changes, right? So we can think of, like, let's say this is the some kind of like a coil with n turns, basically with the same area rotating in a magnetic field with some constant angular velocity omega, such that the theta here is equals to omega times t. That means the kind of like it's not speeding up or slowing down, it's kind of rotating at constant rate. So then you can use one of the equation for the rotational dynamics, where uniform rotational motion gives you theta equals omega t. Now, taking that, let's say, for example, at t equals 0, theta equals 0, then you can look at it in terms of this equation. If I do this derivative with respect to theta, then this equation for change in flux as a function of time will be equals to BA, derivative of cosine theta is then negative sine of theta. And then I replace theta in terms of omega t, becomes negative BA sine omega t. Now, then I can say that EMF, induced EMF, equals negative change in flux, where change in flux equals, I can put like n as a number of loops. So negative n times negative BA sine of omega t. And by the way, there's going to be another omega here when I do the derivative, because if I'm doing the derivative of cosine omega t, so it's derivative of cosine and then derivative of the argument. So sorry, I missed putting omega over there. So once I do the derivative, there's negative omega BA sine theta. That means there's an omega over there. The negatives cancel out. So induced EMF is equal to then N B A omega sine of omega t. Okay. Now from here, what I can do is I can then take the coefficient in front of the sine function to be then the maximum EMF. So maximum EMF then equals to N B A times omega. N is the number of loops, B is the magnetic field, A is the area, omega is angular frequency, where omega can also be written as 2 pi times F or 2 pi over the period. And I can also look at it in terms of how the EMF changes as a function of time for the AC circuits, where it fluctuates, sinusoidal like that, because the sine function, right? So this is being its amplitude, the maximum, let's say EMF, and then after that it fluctuates as sine omega t. All right, so let's look at an example here. So EMF induced in a generator. All right, so the coil in an AC generator consists of 8 turns of wire, each of area, well, A equals, there should be A equals to that, ignore that 5, A equals to 0.09 meters square. And the total resistance of the wire is 12, sorry, some typo, should be 12 ohms. The coil rotates in a 0.5 Tesla magnetic field at a constant frequency of 60 hertz. By the way, the 60 hertz is pretty much the frequency of most of the generators in the US. Europe can have 50 hertz, but pretty much a majority of the, the generators in US operate at 60 hertz. We're going to find the maximum induced EMF in the coil, and what is the maximum induced current in the coil when the output terminals are connected to a low resistance conductor. All right, so part A is relatively straightforward. The maximum induced EMF is EMF max equals NBA omega. Okay, so N is 8 number of turns. Magnetic field we're given as 0.5 Tesla. Area given as 0.090 meters square. And then omega is 60 hertz. Now, 60 hertz is not angular frequency, it's a linear frequency, but linear frequency and angular frequency are related with this equation, omega equals 2 pi f. So I can say it's 2 pi times 60 hertz. Okay, so do this calculation, we should get 136 volts. Okay. Part B, it says, what is the maximum induced current in the coil when output terminals are connected to a low resistance conductor? And that's basically, 12 ohms. Again, all we have to do is just, find the maximum current from the maximum EMF and the resistance in the circuit. That means it's 136 volts divided by, 12 ohms to get 11.3 amps. Okay. Next, let's talk about motors. So this is opposites of the generators. That means what we do here is we have a energy that transfers by electrical transmission into motor, and then energy transfer out by work. That means what we do here is we provide the motor with some kind of electricity, right? So it has to be connected to some kind of, power source. That means we supply it with some kind of electrical, energy, and then it converts that electrical energy into mechanical energy. So basically, you can say, right, generator operating in reverse of, the motor operating in reverse of a generator. So in terms of pretty much, taking mechanical work and converting it into electricity, it takes electricity and converts it to mechanical work. And one of the things we have here is that the motors pretty much comes in, very similar, sort of like, let's say, a setup that we have for the generators. That means they're, pair of magnets, and you have some kind of a loop that rotating, and that loop pretty much connected to the um, commutator that pretty much allows that the motor to freely rotate. And when it starts rotating, you basically have pretty much same idea, right? So you have a change in flux, induces EMF in the coil, and then in EMF that is being induced basically starts inducing current in the circuit. And then one thing we have here is that most of those can be thought of as solenoids. So whenever we're dealing with the solenoids, which we'll see especially in the next chapter, there is what we call back EMF, which basically the EMF that is generated from the coil itself that tries to oppose the current in the circuit. Okay, and usually it tends to reduce supplied current. Remember, the idea here is we are receiving a current, right? As I said, right? So for the motors, they're different from the generators, is that we have to connect this to some kind of electric supply. And when the current comes from that power supply, the loop itself tries to oppose it by generating what we call back EMF, which is basically generating its own induced EMF, which is in the opposite direction of the supplied current. Okay. And the voltage available is basically that you have from the power source. Then the loop itself generates a voltage that is in the opposite direction to supply, to be able to supply this back EMF. Generally, you can think like this. So if you have some kind of solenoid as a device, right? Something like this, for example, and you have a current coming in, then what we have here is the current induced will be in opposite direction. Will be in opposite direction. In order to do that, then you have to have sort of like, let's say, different polarity uh, induced EMF, right? This back EMF is due to this, induced EMF that kind of like, let's say, so if this is a power supply where this is plus, this is minus, you can see that this device, which again, we're going to study this in greater detail in the next chapter, the what we call sort of like a inductor, right, as a device, but still it's just a solenoid, there's some kind of loop, n number of loops put together. So it tries to um, fight off this, this current. Okay. And what we do here is then the current then, because it starts rotating or because of the torque, right? Torque acting on the current carrying coil, it will start to make it, rotate. So then the current in the rotating coil limited by this, back EMF. That means it's trying to reduce the rate at which it's rotating. Okay. But what we have here is that, the coil will begin to rotate, and it's going to then increase the speed, right? Increase with the speed of the coil. It still try to oppose the applied voltage, and eventually the current in the coil will decrease. Okay. Now, one of the things we have here is this device, you can see, right, is eventually connected to some kind of, you know, um, other device that can start doing mechanical work, because as you rotate, the motor, then you want to, basically use that rotational motion to do some kind of useful work. So it's going to be connected to maybe, like, let's say, I don't know, some kind of blades or something like that on the other side. It's going to start rotating because of that. That means what we're doing here is we're taking the electrical energy from a power supply, and then we're using it to rotate basically our motor. And that motor pretty much uses that rotational motion, right, to convert to basically some kind of mechanical work. That's kind of like which is the exactly opposite of the generator. So the generator, you have to do mechanical work, then use that to supply electrical energy to the system. Here, the system takes electrical energy and supplies mechanical work as an output. And so, like, here's an example. Say we have a battery that provides things like this. So here's a battery. This is a positive terminal. This is a negative terminal. And there's a sort of like a conductors that come like this, and then another conductor that comes like that. And then we put this, this n number of coils that put together, right? It's just a, copper wires, couple loop. You can see, right? It's just attached. So there's kind of like You can see, right, there's sort of like a support like that over here, just support like this, where you just place that um, copper wire, like, that is, wrapped around like that. And then you put a magnet, and that's a magnet. So when there's a current in the circuit, that means, basically, because it's a battery, right? It's a DC. So you put it there, and there's a current, which is going to be basically in this direction. But then there's also a magnetic field. For example, if there's a magnetic field like that because of this magnet, then the magnetic field going to apply torque. As it applies torque, then it's going to rotate like that. Okay, so this is pretty much electric motor. So we're using electrical energy from the battery, with a combination of magnetic field, right, to rotate this, copper wire. So let's then talk about what we call eddy currents. So these are generally sort of like, let's say, look at the setup that we have. Again, you have a system where there is a south and north magnetic sources that can generate, let's say, a magnetic field in this region like that. Okay. And then what you have pretty much a moving conductor. So you can see, right? So your conductor here connected to some pivot point, and your conductor then as a pendulum, act like a pendulum, like you just go back and forth through that region where there's a magnetic field. Okay. One thing we have here is, so if you think of, like, let's say there's this region where there's a magnetic field, as soon as it enters this region, you can see, right? So this is the area of the plates. So as soon as it starts entering the region where there's a magnetic field, well, then the magnetic flux through that, through this area will start changing, because now there's more and more and more and more magnetic field through the area as it passes through. Because let's say here, these are the plates. And for example, if this is the magnetic field like this into the page, see, right now there is no, induced EMF or induced current in the conductor. Okay, so there's nothing in the conductor. Make sure that it's connected. But as it goes closer and closer, so let's say when it starts, then, for example, some parts of it then enters the magnetic field. You can see, right, there's already now magnetic field through the area of that plate, which means the plate right away, all the charges in the plate will try to, force that, will try to, basically fight that. And what they will do, they will generate their own magnetic field to try to fight it. You can see, right, the magnetic field that they have to generate should be out of the page. So this is the magnetic field that they're going to generate, which is out of the page, to cancel the magnetic field right now going into the page through the metal plate. Well, in order to do that, there has to be a counterclockwise current. Okay, so that's why you can see, right, there is a counterclockwise current. When it's going to go through the region, we're going to enter that region where there's a magnetic field, sort of like, let's say, from north to south. Okay, so but then when it's right here and it's exiting, then you are decreasing the number of field lines through the conducting plate. Now it's going to try to do the opposite. It's going to try to pump more magnetic field into the page, because now you're decreasing the number of field lines, which is going to make then current, inside the plate to be in opposite direction. Again, using the right hand rule, you can see, right, your fingers will be rotating like this in order to give you your thumb into the page. Okay, so that means now you're going to have a different direction of the, let's say, current. Okay, so those type of currents are known as eddy currents. Okay, those circulating currents. That means circulating currents induced in both pieces of metal moving through a magnetic field. So here's one thing we have again. So you can remember, Lenz's law tells us that induced current must provide its own magnetic field out of the screen. And one thing we have here is, because there is a now induced current, induced EMF in those conducting plates, they actually generate this, what we call retarding force, okay, F of B, because now there's a moving conductor, inside the, let's say, magnetic field, And we know that when there's a moving conductor inside a magnetic field, there's a magnetic force. And that force always going to be produced such that it's sort of like a retarding force. That means when plates entering this region, the force is going to try to slow it down. When they're exiting, again, it's going to try to prevent it, so slow down. It's retarding or restoring force. So like, let's say, one thing we can do here is to minimize the effect is basically make some, let's say slots. So you can see, right, those are kind of like a slots cut inside the conducting plates. Well, they kind of minimize this eddy currents, which then can minimize this retarding force. Okay, that means if you want it to go back and forth without kind of like slowing down too much, you just basically make those cuts, right, in the conducting plates, and that can definitely greatly minimize the effect of eddy currents. Generally, those eddy currents are most of the time not something we want, right? That the unwanted, effect, especially when, for example, you have a patient in an MRI machine and things like that. So those eddy currents technically can be, something that is undesirable. So we can try to minimize those effects and things like that. And they can affect, the machine or even nearby equipment and all of those things. So those are pretty much the effect of the conductor moving through the magnetic field. And we know, right, that there's always a force acting on a conductor when it is moving and there's a magnetic field. The idea here is that because it's moving, so there's a change in flux. Remember, that means this happens only this part and that part. When the conductor is here, the current technically inside the conducting plates are zero, because you have a steady magnetic field through the entire region. So the magnetic flux is constant. Only when it's entering and exiting, then you have that, induced EMF and induced current. It means, remember, the idea here is only when something changes. So that means when the conducting plate is just entering, you then start increasing number of field lines, that going through the plate, it induces current. Then there you have this retarding force. When it goes through the region, when you have the maximum, so like let's say maximum amount of electromagnetic field already through the plate, the flux doesn't change. There is no induced current. And then when it's exiting, then again same thing happens, because when it's exiting, it tries to prevent, change in flux, and then induces, current in opposite direction. All right, guys. So that's it for this chapter.